Good morning, everyone. Anybody have any questions before we get fired up? No questions? All right, well, I want to let everybody know our midterm was what, chapters 1 through 8. So every 2 chapters, I generally do a test. So I'm probably going to open up an online test maybe Wednesday or Thursday, and it'll be due Sunday. And that'll be on, basically chapters 9 and 10. But of course, they're always comprehensive. So there'll be some stuff from previous tests and stuff like that. So be prepared to get one of those done. You also have your normal homework to do and all that stuff, so don't get too far behind. It's the way it's been working out. We've been having something, 1 or 2 assignments due on Wednesday and 1 or 2 assignments due on Sunday. So make sure you pay attention to the MyLab and mastering deadlines. I've updated those on Friday just to make sure everything was on the same, we're all on the same page. So 36 and 10 are now appropriate. So 1 through 10 and 36 are all correct dates. Nothing later than 36, of course. And by later, I mean other than chapter 36 and 1 through 10, nothing means anything on mastering because we haven't covered any of those chapters. So last time we were discussing, since it appears no one has any major questions or anything, I guess we'll go ahead and get started.
I'm sorry, sir. I just hopped in. I did have one question for you.
Okay.
Which was it? Here it is. It was the irregular object of mass m, and then the moment about parallel axes near and far to it.
Right.
I was just wondering how exactly to calculate those, because I don't remember seeing something for that.
Did it? I think the problem probably gave you a moment of inertia about its center of mass.
Yes.
Then all you have to do is add to that moment of inertia mh squared, where h is the distance between the center of mass and the parallel axis.
Oh, because like moments are just added like linearly, basically.
Sort of, but there was something we covered called the parallel axis theorem. I remember I used it to find the moment of inertia about the end of a rod compared to the moment of inertia about the center of a rod. We calculated the moment of inertia about a center of a rod was 1/12 ml squared. But then if you rotated about an axis parallel to that, then but put it at the end, then the distance moved was half a L. So now you have a parallel axis here that you're going to rotate it about instead of the one that you calculated. So you end up getting 1/12 ml squared plus m times parentheses L over 2 squared. That ultimately changed it to 1/3 ml squared. So yeah, it's a parallel axis theorem, but moments of inertia do sort of add that way. Like if you have several things all with the same center of mass, all sort of connected together, you can add them up like that. That complex Atwood machine I had, basically there was like a cylinder whose center was right here, and then another cylinder who was bigger, but its center was that same axis, and they were stuck to each other. Yeah, you just add those in that case.
Gotcha. All right, thank you.
No problem. All right, so as I was saying last time, we learned basically the origins, some of the history of and the origins of the special theory of relativity, and basically it was relied on 2 fundamental postulates. The first postulate being the laws of physics are the same for all inertial observers. I explained to you how Einstein used that inertial observers phrase to cut out gravity. And then the second one was that the speed of light is a constant independent of the motion of the source of the observer. And so doing that, we were able to derive an effect called time dilation. And time dilation basically says that moving clocks move more slowly. So dilation, remember, actually means like when your eyes are dilated, that means the hole in your eye got larger. So what they're saying is time intervals get larger. And that sounds kind of counterintuitive to what we were saying as time dilation, but just imagine it this way. Imagine you did like 1 million experiments with this perfectly machine robot made ice cream cone, that once the machine made it, you could time it, and the instant that it melted all the way down so it was just a blob of liquid inside the cup, and then of course everything that fell beside it, that on average that was a 20-minute ice cream cone, and that the standard deviation was really, really small. So you expect basically all of them to reach that same point right at 20 minutes. Now, if you and someone on a train car traveling at, let's say, 86.6% of the speed of light, both are teleported a 20-minute ice cream cone like that, then you will believe your ice cream lasted 20 minutes and they will believe their ice cream lasted 20 minutes. But you, looking at them on the train car, would say, in fact, that their ice cream cone lasts 40 minutes. And they would look back at you and say that your ice cream cone lasted 40 minutes. And they're both right. Okay. That's the weird thing. They're both right. But that's the way relativity works. It's the person on the train is moving relative to you, so their time is slowed down according to you. But according to the person on the train, they're sitting perfectly still, and you're flying by them at 86.6% of the speed of light, i.e. root 3/2. And they said your ice cream cone is going to last 40 minutes. That sounds contradictory and everything, but that is actually the way nature behaves. We've done numerous experiments with this. Special theory of relativity is the single most tested theory in the history of mankind. So it really reaches that golden standard of theory now. It's no longer a hypothesis. For instance, we build large accelerators, and accelerators have collisions sometimes tens of thousands or even at least hundreds every second. No human can watch those. So we have to write computer programs that actually look for anomalies when we're running those experiments. And those experiments often run for months on end. And there's, several tens of thousands of accelerators around the world, and they've all been going since the 1950s. So you can imagine that basically this special theory of relativity has never been violated by any of those things. So it's literally been tested on the orders of hundreds and hundreds of millions of times. So yeah, the special theory of relativity is solid. There's nobody doubts the special theory of relativity. We might discover some other theory later on that maybe changes it to the fourth or fifth decimal place, but in the laws of physics are such that we now use the correspondence principle. If we find another hypothesis that's supposed to take over for special theory of relativity, it's still going to have to give us the results of special relativity in the realm where special relativity worked, which is basically everywhere so far. Okay, so we know it's that good. All right. Now, that's the special theory of relativity, and it gave us time dilation. So let me show you one particular calculation. We know, for instance, that there's these particles called muons. They're created about 1,500 meters above the Earth's surface. And those muons are actually created from solar radiation interacting with our upper level atmosphere. And they create muons basically moving very, very fast. And those muons are actually able to reach the surface of the Earth. Well, if you look at those muons, they're going a pretty particularly high fraction of the speed of light, and they reach the surface of the Earth, but their lifetime is too short at that speed to reach the surface of the Earth. So the fact that they actually reach the surface of the Earth has to be understood only through special relativity. Otherwise, they would not be able to make it. So, and I'll work one of those problems with you a little later, but I first want to work a little bit more with the time dilation equation and give you some ideas of some things that I suggested you do on your own. Hopefully y'all did, but if you didn't, you should still try. I'm going to do something with a spreadsheet, but I'm also going to do something with some algebra. Yes, go ahead.
You said that the theory of relativity is the most widely tested theorem, and I read something recently where there was an article that was very excited about how we saw light curve. It was light either curving around a black hole or around another stellar body of some kind. and it was saying that that confirms the theory of relativity. I was under the impression that that was kind of known, basically, that light is bent by space-time, like by
Yeah,
a gravitational point.
what they were probably talking about in that case is Hawking radiation. So Hawking radiation, and this is probably why he was unable to win the Nobel Prize before he died, he predicted the existence of what we call Hawking radiation near the event horizon of a black hole. And we've done something very similar to that. In other words, we simulated technically similar conditions to the area of a black hole, around a black hole, doing so with optical things, where basically an area that was unable to be escaped by light. If you create that at, here on Earth, even though it's not a black hole, just as an area that when light goes in, it can't get out. They've seen that type of radiation coming in there, and it looked like Hawking radiation. But again, that wasn't exactly Hawking radiation because it was just equivalent to it, and it wasn't around a black hole. That was sort of the bum part about Hawking radiation, is we probably weren't going to have enough evidence directly from a black hole because the light is so weak. Well, recently I had read some things where they were actually testing and looking for Hawking radiation, because we've now been able to actually physically take a photograph of a black hole, or at least of the radiation coming from the black hole. So that's,
I do remember that was a big deal.
Yeah, that was a huge deal. In fact, it was done. It's really cool. It's a cool story. It's done by well, I say a little girl. I mean, she's grown. She's probably finished her PhD now and probably teaching somewhere. But it was a person that, as a little girl, she said she wanted to be the first person to take a photograph of a black hole, and she, lo and behold, did so for her PhD thesis, and got a photograph of a black hole. So that's kind of cool. And since then, we've done it several times, but we've been able to now to get so well at it, so good at it, that we've actually been able to detect certain types of radiation. And we believe we might be on the cusp of seeing Hawking radiation.
Okay, I was just curious about that.
No problem. Yeah, and that's actually Hawking was really flirting around the edges of tested theories when he came up with that. He was combining quantum mechanics and information theory, and combining that with what we know from cosmology and what we know from general relativity. So it was really a monumental thing to make a statement about, and it seems like he predicted correctly. So that's kind of cool. Right. All right, so here's what I wanted to mention to you. So we derived the time dilation equation. Pretty straightforward. It's just basically algebra and knowing a little bit about right triangles and stuff like that, and then applying that weird principle that the speed of light's a constant. So let me switch to my document cam and show you something neat. So what we found was that the time interval by someone that sees another person moving, so the time interval for you on the bank of a railroad track, is equal to gamma times the time interval delta t0, called the proper time, that is the time interval measured by a person on the train. Okay, and it's proper because it would measure the clock that is measuring delta t0 is not moving relative to the person. So this one obviously is moving relative to the person, because this person is looking at that person's timepiece. So that's why that's not proper time. And we found that gamma, of course, was defined to be 1 over the square root of 1 minus v over c squared, which is also 1 over the square root 1 minus beta squared. But you can see this is always greater than or equal to 1. And we also know that beta is defined to be v over c. So I suggested one of the things you should do is probably, since we know gamma is going to be greater than 1, find out what values of beta yield whole number gammas. So gamma equal to n for n equal, well, 1 is obvious, but we'll start with 2, 3, 4, 5, 6, on up to 10, maybe 100 from there, maybe 1,000, maybe 1,000,000. So some really staunch whole numbers. Okay, these are really nice things, and they allow you to quickly do neat little relativity examples in your head. So for instance, let me show you how to compute that. I like to do it algebraically, because when you do it algebraically, then you can algebraically look for actual exact answers to beta, and instead of just decimal places. Normally you have to deconstruct it to figure out what decimal it is, but if you do it algebraically, you can find it. So I'm going to take both sides of this and square it, but I'm going to use the beta version. So it's going to be gamma squared is equal to 1 over 1 minus beta squared. So that's what happens when I square both sides. Now I'm going to multiply both sides by 1 minus beta squared and 1 over gamma squared. So I'm going to get 1 minus beta squared is equal to 1 over gamma squared. Now I'm going to solve for beta, and I'm going to get beta squared is equal to 1 minus 1 over gamma squared, which you can also write as gamma minus 1 over gamma squared. So beta would in fact equal the square root of gamma minus 1 over gamma. So that's a nice, neat expression. So all I really want is this to be a whole number. So if I set this equal to 2, let's say 2 is equal to the square root of gamma minus 1 over gamma, then I'll get 4 is equal to gamma minus 1 over gamma squared. And I can now say this is going to be 1 over gamma minus 1 over gamma squared. That's not necessarily the best way. I'll multiply it through by gamma. Let's say 4 gamma squared is equal to gamma minus 1. Now I'll get the gammas on the same side. And I'll say 4 times gamma squared minus gamma is equal to 1. I can factor out a gamma. I can say gamma times 4 gamma minus 1 is equal to 1. That doesn't help me too much. So it looks like I'm going to have to say 4 gamma squared minus gamma plus 1, or excuse me, minus 1. Is equal to 0. So that's a quadratic equation. We can say gamma equals negative b, that's negative of negative 1, plus or minus the square root of b squared, that's negative 1 squared, minus 4 times a, which would be 4, times c, which should be, we concluded that was negative 1. Still looking like a positive over here. Times negative 1, which is good because it keeps us from getting the negative under the square root, over 2a, this should be 2 times 4. So I can get 1 plus or minus the square root of 1 plus 16 over 8. So it's 1/8 plus or minus the square root of 17 over 8. I'm 100% certain I made a mistake here because I'm pretty confident it's supposed to be root 3 over 2, but that's sort of the scenario we're going at. It is. Y'all can look for that error if you want. I've solved this a million times, but for some reason it just went to crap. It's most likely an error or a error. Because look at this, if I actually try beta equals root 3 over 2, then gamma is going to be 1 over square root 1 minus square root 3 over 2 squared, like that. This pen looks like it might be dying. So it'll be 1 over the square root of 1 minus, when I square root 3, I get 3. When I square 2, I get 4. So 1 minus 1 3/4 is 1/4. So that's 1 over the square root of 1/4, which is of course 1/2, and 1/2 in the bottom becomes 2 in the top. So that's what I should have got, was root 3 over 2. So that's why I know it's an error in here somewhere. I just don't know what I did wrong. I probably flipped a negative or something stupid over here. But anyways, y'all can go ahead and do that if you'd like. But now you know why I said 0.866, 86.6% of the speed of light is beta. And that's equal to, if you carried it to an infinite number of decimal places, it'd be equal to √3/2. So I know off the top of my head that √3/2 is in fact a beta value that gives me a gamma factor of 2. So that means it's going to make my time intervals twice as long. So that's sort of the advantage of doing that. The main part I'd focused on, as opposed to practicing doing this, which I should have done, the main part I focused on was doing this, which was you can take I want to share my screen for a second. You can take a spreadsheet and make a simple formula when you actually solve that gamma. And then you could put in, for instance, the value of 1, or excuse me, not 1, let's say 2. Whoa, a little delay here. Let's say 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoa. Well, that was stupid. 10. And then you could do 100. And then you could do 1,000. And then you could do 1,000,000. So on and so forth. And with the proper formula for solving for gamma, which I'm going to attempt again, hopefully a lot quicker. So gamma squared is equal to 1/1 minus beta squared. That gives me 1 minus beta squared is equal to 1/gamma squared, which gives me beta squared is equal to 1 minus 1/gamma squared. Oh yeah, I see where I did. Right, when I did this part, that was where the error was. So let me stop sharing my screen real quick. Okay, when I did this part, this is where the error came in, because I made this gamma minus 1/gamma squared. That would have to be gamma squared minus 1. That's where the mistake came in. So at this point, I can automatically tell. Go ahead. Who was that?
That was Kevin. I was just saying where.
On this, when I was doing this right up here, you see I called this gamma minus 1/gamma squared. That should have been gamma squared minus 1. So there's the error. So now that we have that in our notes for what the error is, we now know beta should be this, which you can also call, again, we can say that's equal to gamma squared minus 1/gamma squared. We'd say beta is equal to the square root gamma squared minus 1/gamma squared, which would be the square root of gamma squared minus 1/gamma. This was supposed to be a squared there. Okay. So now I can plug that formula in, go back to sharing my screen. Okay, so these are values of gamma. And therefore, I should take this formula and say this is equal to, what we want is gamma to be this value over here. So I'm going to say square root of this value squared minus 1 divided by this value again. And this will give me, oh, no, where I had a minus there. Oops. Whoa, what happened? Okay. Square root, oh, gamma squared minus 1. That's, I had the minus, but I never typed in the 1 evidently, or my mouth, what keyboard didn't work. Yeah. So there's the 0.866025, which is √3/2. And you can see if you really want to get up to 1,000, you're looking at 99.9999. I think that's 1, 2, 3, 4, 5, 6, yeah, 99.9999 to get to a factor of a million, or excuse me, to get to a factor of 1,000. So in other words, if you left on a spacecraft traveling at 99.9999% of the speed of light, and let's say you left your twin brother back on Earth, okay, after you had traveled for 1,000 years, according to your brother, you would only be 1 year older. Now, that doesn't mean you and him could communicate too well necessarily, because for starters, at 1,000 years, he's dead. But if you had a infinitely fast delivery system, which relativity says you can't have, then you could call him up if he had lived and say, well, how old are you now? And he'd say, 1,018. And you'd say, oh, really? I'm just 19. So, but that's a kind of neat little table to have. So these are basically all the different betas. You can see 86.6% gives you a gamma factor of T of 2, 94.3% gives you a gamma factor of 3, 96.8 gives you 4, so on and so forth. So that's kind of a neat little thing to have. Actually, I find it a little more useful doing it like I did here, just by hand, and then choosing the ones that are going to give me whole number square roots. And that gives me a little bit more useful stuff. And if I do those by hand and actually come up with those decimals that I have on my spreadsheet, then I tend to remember them a little better. So does that make sense, everybody? This gamma factor appears over and over and over again in relativity, and we're going to use it over and over again. For instance, we're going to find that there's something called length contraction, and that length contraction is going to have a factor of gamma in it. So you're using it for that. We're going to find that kinetic energy is not 1/2 mv squared. It turns out it's going to be gamma minus 1 in parentheses times mc squared. You're going to find momentum is not mv, but gamma mv. So this gamma factor is going to appear over and over again. That's why I said it's good for you to become familiar with it, become familiar with the algebra, which I really am, even though I clearly made a boo-boo jumping there on that stuff. But anyways, let me stop sharing the screen. So y'all can make this at any time. It's not that big a deal. I do recommend you do it at some point, just either for the spreadsheet to have the numbers that you can quickly refer to, or do it algebraically so you can just get a little bit more familiar with working with this kind of algebra.
You kind of lost me somewhere in the derivation. When we changed the I forget what that
you talk about the training last time?
Huh?
He said
no,
derivation.
In this right here where you're
gotcha.
writing out the math. What is that? Is that 4 gamma, or is gamma the big B?
So gamma is that big nasty formula, 1 over the square root of 1 minus v over c. But to ease writing, we often write it as 1 over the square root of 1 minus beta squared.
Okay, so beta. All right, so where you wrote 4 gamma squared minus gamma minus 1, that should have been 4 gamma squared minus gamma squared minus 1, so it'd come out to 3 gamma squared minus 1.
Yeah, and then I would have gotten 3/4, and then you have to take square of that, you get root 3 over 2, which is exactly what we found just now with the 86.6 when I made this equal to 2, or excuse me, this equal to 2. So that's the error. It should have been a 2 there. And you see when I go through all this, yeah, that 4 would have ultimately been 4 squared minus gamma squared, which would be 3 squared. Or excuse me, yeah, it'd be 3 gamma squared. So yeah, that would actually work it out, and you'd end up getting back what I said, which was root 3 over 2.
Where would you get root 3 over 2 exactly? I tried plugging that in, and I got the solution as 1 over root 3.
Okay, actually, I don't know if I made another mistake somewhere along here. We found this mistake, right? We found this mistake. And I was going on assumption when you told me you read that when you put a squared here, that would work out. And I could see it working out to be roughly root 3 over 2. But that's just because I had a 4 gamma squared minus gamma squared. So I didn't really test that to go on, but it should have gave me gamma equals √3, or excuse me, should have gave me beta equals √3 over 2. If I want to see that here, I just say square root 2 squared minus 1 over, this isn't under square root, so I should really put it there. So I just say over 2. So you can see 4 minus 1 is 3, so it's square root of 3 over 2. If this worked, if I didn't make any more mistakes, then it should have came from this point. It would have went, I've got beta squared in terms of this, so I just take the square root of gamma squared minus 1 over gamma and just be b. Okay, yeah, so I wouldn't even need to have gone through all this. This was where I was doing a lot of other stuff. So it would have worked out to be the right thing. No telling what happened in here though. So, but this shows you it does give you √3 over 2, which is approximately 0.866025. Okay.
So I guess all that we really need to remember is that final formula there.
I wouldn't even waste my time memorizing it. The algebra is usually so quick that you just work through it. You should know what gamma is and what beta is, and just be prepared to use that. I've hardly ever asked you to solve something like what is gamma, or what beta gives you gamma equal to 12. I don't normally ask you to solve that sort of thing in a problem, but you can just through experience. So what you need to remember is the principles of relativity and this time dilation equation and the definition of gamma. And just be prepared. Sometimes people would just say, beta, or they'll say 36% of the speed of light. What they're giving you there is beta equals 0.36.
Okay, I'll just ask you a little more after class, because I'm still a little lost as to, I guess, like what I'm supposed to take away from this page.
The page of writing or the page of the spreadsheet?
The kind of both. I mean, like, I understand what you're getting at, where it's what were you saying? You were like, gamma is the factor by which time
things expand or contract.
Flowed.
Right.
Yeah, like I can kind of understand that, but I'm having trouble kind of attaching it to a concept in my mind.
Gotcha. Let me do something real quick too. I'm gonna all right, so I'm going to solve a problem real quick. So what we find is muons are created by interactions at the upper atmosphere. H about 1,500 meters. And they often are detected at the surface of the Earth. Despite having a 2.2 microsecond lifetime. So what we're seeing is these things live a very, 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 very short life. Okay. And it turns out they still, living only 2.2 microseconds, they still make it to the surface of the Earth. And if you just consider how fast they're going, you'd say that speed is too small for them to reach the surface of the Earth. Let's say that speed, in fact, is about 6.9, or excuse me, let's say 6.5. Their speed is, let's say 6.2 times 10 to the 6th meters per second. How do they make it? So that is according to us. How do they make that? Well, if you took distance equals velocity times time, and you did 6.2 times 10 to the 6th meters per second, and multiplied it by 2.2 times 10 to the negative 6 seconds, I think you can see what happens is 6.2 times 2.2 gives me 13.6, or 1.360 kilometers. But this thing's supposed to be 1.5 kilometers, right? So how does it make it? Well, the answer is time dilation. Specifically, the delta t that it experiences, which is delta t0, is actually quite a bit longer because we see its clock moving so much slower. So in fact, what we see its lifetime being, delta t, should be equal to 2.2 times 10 to the negative 6, its lifetime, over 1 minus beta squared, which is 6.2 times 10 to the 6th over 3 times 10 to the 8th squared. And that turns out to be more, obviously, than 2.2 times 10 to the 6th. Let me see. I just made these numbers up, so there's a high probability I screwed something up. But anyways, 2.2 e to the 6, excuse me, e to the negative 6, divided by, now I'm going to take the square root of 1 minus, oh, yeah, I did screw up. I was supposed to be 620 times 10 to the 6, not 6.2 times 10 to the 6. I was literally off by a factor of 100. Dang it. All right, let's kill that.
Just change the 10 to the 6 to 10 to the 8.
Yeah, 10 to the 8th would be better. Because, yeah, and that would make that number work out right too. I was getting a weird exponent on this and I couldn't make out why. And it's because of this. Yeah, change that 10 to the 6 to 10 to the 8. Sorry about that, everybody. And that's going to get 6.2. (6.2) e to the 8th times 2.2 e to the negative 6. Yeah, that gives me 1.36. So that is the 1.36 times 10 to the 3 meters, which is 1.36 kilometers. Okay, so that's exactly what I expected. Whereas I need 1.5 kilometers, I'm not quite there. Now, when I change this down here to 10 to the 8th, you can see that the lifetime that we think the muon lives is actually dilated, i.e. made bigger by this factor. I know that's hard to read, so I'm going to say it out loud to you. This is 2.2 times 10 to the negative 6 over the square root of 1 minus parentheses 6.2 times 10 to the 8th over 3 times 10 to the 8th, which is the speed of light, in parentheses squared. So now I'm going to do 2.2 e to the negative 6 divided by square root 1 minus parentheses 6.2. Whoa, that can't be right.
Yeah, I was going to say 6.2 times 10 to the
That's
8
twice
is
the speed of
double
light.
light
Yeah.
speed. Yeah.
Yeah. Let's just throw this example away. I don't know what Mr. Younger did, but there was a definite problem. I'd written all these facts down, and about the muon, for instance, like I'd written down the fact that the muon has a half-life of 2.2 times 10 to the negative 6 seconds, and that it's found, I actually found several different speeds. That was the problem. I was trying to find a speed to work this out, but it's actually a lot more complicated. It turns out when the upper atmosphere is basically the solar radiation coming from the sun and the solar wind coming from the sun, when they interact at the upper atmosphere of the Earth, it actually creates muons, and then the muons come down anywhere from, I think your book uses an example of 60% of the speed of light, and that of course works. And if you, for instance, I'll show you that, how far can a muon travel? I'll make this as a better example. Travel at beta equals 0.60. Remember beta, and the reason I'm doing this is showing you how they often will state something. They'll just say 60% of the speed of light, or they'll say at beta equals 60. This means 0.60 c. Okay, so that's our question. How far can it go? Well, distance equals velocity times time. If you ignore relativity, that should be it. So I'm going to say 0.60 times, remember the speed of light is technically 299,792,458 meters per second exactly. And then times 2.2 times 10 to the negative 6 seconds. That's the half-life, or that's the mean lifetime, if you will. So when I do this math, this will definitely be right. So we can at least take some solace in that, because Mr. Younger's obviously having a bad day. 0.6 times 299,792,458 times 2.2 e to the negative 6, and I get a distance of about 395.7 meters. Okay, so this thing should be able to travel about 400 meters, but like I said, it's created 1,500 meters up. So how are they reaching the Earth's surface? Lifetime, I just write it here just to remind everybody. Lifetime is 2.2 times 10 to the negative 6 seconds. Okay, well, the answer is time dilation. We know that its moving clock, its internal clock, in other words, the thing that tells us its lifetime is 2.2 microseconds, we know that that clock is moving with respect to us. So our time measures delta t equals gamma delta t 0. Well, gamma is equal to, and delta t 0, 2.2 times 10 to the negative 6. That's the delta t 0. But the gamma is 1 over the square root of 1 minus 0.60 squared. Everybody see what I did there? This is just 1 over the square root of 1 minus beta squared. So I'm going to say 2.2 e to the negative 6 divided by square root 1 minus 0.6. I'm sorry for being so sloppy on that earlier. This gives me 2.75 times 10 to the negative 6 seconds. So we say its lifetime is actually 2.75 microseconds instead of the 2.5 instead of the 2.2. And in fact, using 2 sig figs, you really should round that up to 2.8. But now we can look and say, oh, well, distance is equal to velocity times delta t. Now we get 0.60 times, let's just call it 3 2.0 times 10 to the 8th meters per second instead of writing all those digits. And now I'm going to say times 2.75 times 10 to the negative 6 seconds. And hopefully that'll give us something 1500 meters or larger. So now I'm going to do 0.6 times 3 exponent 8 times 2.75 e to the negative 6. And actually that gives me still like 500 meters. So at 60% of the speed of light, it's still not fast enough to make it to the surface of the Earth. So that one must have been one created as a secondary reaction or something like that, since it was only moving at beta equals 60. This was the reason I didn't want to use beta equals 60, because it gave me a distance, or I thought it would have given me a distance of smaller than 1500 meters, as it did. Okay, so if you really want to know how much time it needs, you're going to try how much time does it need? How much time does it need, or speed does it need? You see in this problem, if you try to work it this way, you've got two variables, both of which are affecting each other. So that's the rub. But if we bump it up to say, we found this only went, what, 500 meters at 2.75. So increasing it by what, about 0.5 microseconds, which is really about 25%. So if I increase it even more, I would want 3 times as much distance, right? Because that would give me the 1500 meters. So I need at least, if this was the time, the lifetime, I would need at least 3 times as fast. But you see, if I made it 3 times as fast, I would probably get more than 3 times as long a life. So I might not need all 3. But if I tried that, that would possibly work. So what I'll do is I'll refer to my gammas, share the screen for just a split second. Okay, I'll refer to my gammas and say, well, I did 25% of the speed increased. In other words, by going from just non-relativistic to 60% of the speed of light, I gained basically about 25% of the lifetime. So maybe I should try like a factor of 3 in the gamma, because 3 in the gamma would actually give me 94.2%. Or I could do 4 in the gamma. So yeah, let's take 4, 96.8. So let's try 96.82. So I'm gonna stop sharing. Let's try V equals 96.82% of C. Okay, so when I try that, I'm now going to see the lifetime of the muon is going to be 2.2 times 10 to the negative 6 seconds divided by square root 1 minus 0.9682 squared. Notice that percent, if I make it to a decimal, that just becomes a beta. That's why I just put that in there, and I didn't have to put any C's or anything. So now I'm going to say, my calculator ever turn around, 2.2 e to the negative 6 divided by square root 1 minus 0.9682 squared. And this time it gives me 8.793 times 10 to the negative 6 seconds. Okay. Now, if we do that, then the distance would be 0.9682 times 3.00 times 10 to the 8th meters per second times 8.79 times 10 to the negative 6 seconds. And I get 0.9682 times 3 exponent 8 times 8.79 e to the negative 6. And that gives me 2.55 times 10 to the third meters, which is 2.55 kilometers. So that's more than enough. Okay. So you can see, just as a result, the main physics that we're learning here is that moving clocks move more slowly. And because of that, the muon's lifetime is extended, as is mine. If I got on a spacecraft moving at 86% of the speed of light, my clock would move half as fast as yours if you were left here back here on Earth. So every 2 years, I would only age 1 year compared to you guys. That's the big physics principle here. Now, the other problem is, if you'd imagine a who, you know, Horton, here's a who. If you'd imagine a who riding on the back of this photon, that who must also have a very good reason for understanding that it was created 1,500 meters up and hit the surface of the Earth. Because still at, you know, at the atmosphere being 1,500 meters, it doesn't experience any time contraction. The who doesn't, because it's actually on the particle. So it sees the Earth moving towards it. It's not moving. So why, can anybody tell me, why would the who also agree that it made it to the surface of the Earth? Because obviously it would. I mean, the who would literally, you know, be in the collision riding the thing when it hits the surface of the Earth. Anybody have an idea? I hinted at it on Friday. Time is up. Y'all are free to go, but I'm going to give you a couple more seconds to answer a question. If anybody needs to go ahead. This is going to be recorded anyway, so with all my errors. So remember, velocity, which is the speed of light, has to be a constant. And velocity also is distance traveled divided by time taken. So I just showed you one way to make sense of the muon making it to the surface of the Earth, and that was its time had been lengthened. What's the other way I could make the velocity or the distance or the velocity change such that it's consistent with the speed of light? Anybody? Well, we haven't learned it yet, so it's perfectly fine that y'all didn't get it. But according to a who riding on the back of a muon, it sees the Earth coming at it at, in this case, 96.82% of the speed of light. The Earth and its atmosphere is coming to it, so it's length contracted. We call it Lorentz contraction or length contraction. And the atmosphere, which was 1,500 kilometers, is now that same gamma factor different. Okay, and that gamma factor was, I think, 4. So instead of the atmosphere being 1,500 meters deep, it's 1/4 of 1,500 meters deep, which is, you know, a little bit more, a little bit less than 400 meters. So clearly it makes it that way. But that also shows you philosophically how you can't have time dilation without having space being puckered or messed up as well. Because obviously in one frame, time can explain it, but in the other frame, something else is going to have to explain it. And there's really only 2 parameters to deal with in the speed of light, and that's distance and time. We've already used the time, so we had to change the distance. Instead of increasing the time, we could also decrease the distance, and that's what happened. Next time, we'll talk about twin paradox, and I'll do a length contraction problem for the who, for instance. And I'll be a little, even though I put a lot of time into prepping for this, I screwed up, and that made it worse. But next time I'll be a little bit more better prepared for you guys anyways. So I apologize for that. I'll wait for the last person to leave, and you're free to go. Make sure you ask me any questions you have. Gavin, do you still want to, you still have some questions about, you know, why that list of gammas and all that stuff was relevant?
Yeah, sure. So the thing was, I was kind of following the math. Like I've got that equation, gamma is 1/√1 minus effectively %c squared.
Right.
So okay, so let's just I guess start with it again. How did you get like the table? Were you just plugging in? You were plugging in like beta values and then solving for gamma?
Okay,
or was it the other way around?
In the table, let me turn it to that so you'll see what I'm doing here. So in the table, I was looking for gamma values that were whole numbers. So I could easily say, oh, the length is going to contract by a factor of 4, or the time is going to dilate by a factor of 8. So I put gammas over here, and I just chose whole numbers, 2, 3, 4, 5, 6. I didn't necessarily need 11, 12, 13, but it would be nice to know 10, 100, 1,000.
Oh, so you were basically just like plugging in gamma numbers and then getting the percent speed of light.
Yeah, getting the betas.
For the beta.
Yep. And you can see the formula is just square root of gamma squared minus 1 over gamma.
Yeah. Okay. Yeah, I guess that wouldn't be too hard to just kind of, write out, as long as you remember that. That equation, I suppose.
Right. Yeah. You just need the main equation is 1 over the square root of 1 minus beta squared. That appears over and over and over. Sometimes it appears in reciprocal form, in which case it's just the square root part. But the main thing is that is the gamma when you do 1 over the square root, and that gamma is always 1 or larger.
Yeah, because you can't do the what is it? Well, wait.
You can't do beta greater than 1%, for instance, greater than 100, for instance.
Well, I mean, yeah, because you can't do, you would end up with an imaginary number, I guess.
Right. And if you look on that table right there, you see I have a 38.8. Well, in looking up that muon, I actually discovered that the gamma factor for a muon was actually 38.8. So typical muons actually arrive at 99.9668% of the speed of light. But I literally found that just as the camera was coming on with Zoom. So my internet was really slow this morning. That's why I sort of hemmed and hawed and made a few careless mistakes. But anyways.
Okay.
So that's the neat thing. When you have that table, then you can put in any gamma value you want, and it'll spit out the answer. And in fact, you see at 1,000,000, this doesn't even carry enough decimal places. But if I change the format, I could change the format and let it show more decimal places. So format cells, and I'll say numbers, and I'll put maybe 12 decimal places. I think it can do up to 12 anyways. I'll say number 12. Say okay. It's still still 1 to 12 decimal places. So obviously, to get a factor of 1,000,000, it's a really, really, really large percentage of the speed of light.
Yeah. And these are, which of those two are formulas that are in the book? The one where it is beta is equal to those gammas, or the other way around?
I haven't seen no, that's not in there at all. What I have seen in your book, I've seen them use beta, but I haven't seen the symbol beta pop up. But I might just be misremembering.
Well, I mean, in theory, that's just
gamma.
Yeah, I was going to say the gamma equation. The beta equation is just the same equation but rearranged.
Oh yeah, yeah. I was literally meaning beta v equals v over c. But yeah, you're right. It's just, yeah, that's all you really need is the gamma. When I suggest you use this table and stuff like that, that's just for quick computing and to wow your friends, if you will. Like, I'm going to talk about the twin paradox, and I happen to know Alpha Centauri is about 4 light years away. So if I wanted a gamma factor of 4, I could quickly use that table that I just made, or I could quickly do the calculation that I just did, where beta, it would give me the actual beta for gamma equals 4.
Wait, so gamma, and what would that produce? That would be like when you're traveling at this speed that you would perceive that you'd get there in 1 year?
Exactly. It would take basically, since it's 4 light years and you're going a large fraction of the speed of light, 96.82%, it would take you a little bit more than 4 years to get there. But with a gamma factor of 4, that means it just take a little bit more than a year.
So with gamma being 4, you said?
Yeah.
Where is? Oh yeah. So gamma is just
gamma being 4. Yeah.
Gamma is just the change in, it's like the percentage of, what is it? The percentage of the compressed time over the.
It's the multiple of the compressed time. So it's not even a percentage. It's literally you're multiplying that times time. So if you have a 5-minute ice cream and you got a gamma equal 4, that means your ice cream is going to last 4 times 5 minutes, which is 20 minutes.
Well, no, I was saying like if you were to rearrange it, like gamma is equal to delta t over delta t naught.
Right, right.
And so that would be, well, that would come out to like 1/4 or something, wouldn't it? Or...
No, it'd be 4, because remember, gamma is always 1 or larger.
Yeah. Well, no,
so
where I wrote it, where I wrote it, I thought it was delta t is equal to gamma times delta t naught, which is the proper time, as you said. It's
exactly.
It's the so delta t naught would be 4, wouldn't it? Because of 4 years.
Oh, okay. So delta t naught would be the 1 year. That would be your time period spending on that spacecraft flying to Alpha Centauri.
Oh, so t naught is the time. Wait, it's time according to what, the
person that's moving but not moving relative to their own clock. So if you're wanting to know how much time passed, you're looking for delta t. If you're looking for how much time passed for that person moving by you, you're looking for delta t 0.
I'm sorry, say that again.
I said, if you're looking for how much time passed for you, you're looking for delta t. If you're looking,
and for me being the person on the ship, or looking at
for
the ship?
you just being you, whatever time you're dealing with, and then delta t 0 is the time that someone flying by you is measuring. So anybody moving relative to you is experiencing delta t 0, and you're experiencing delta t.
So then delta t is like the outside observer time?
Yep.
Okay. So I was a bit confused. When you wrote proper time, I was imagining that as the time observed by the outside observer.
No, that's always the person who doesn't see their clock moving. So you're trying to figure out what time they're experiencing. Their time experiencing is delta t 0, but what you're experiencing is delta t if that person is going by you.
So t0 is the time experienced by the person that is not moving in relation to their clock.
Exactly.
Okay.
And their clock could be a biological clock, by the way. That might help you a little bit.
I guess that also works. I'm probably easier just to think of it like a, alarm clock they're looking at.
Right.
But and this, okay, so I think I've got a better handle on this. And then this last thing is just kind of whimsy, I guess. And this is we were talking about like spending time traveling a great distance. Would all of this still apply if someone were like vibrating or oscillating at an appreciable fraction of the speed of light?
Yeah.
If they were just kind of doing this, would time still slow down for them?
Yeah, it would slow down both directions. Like if you're on a spring, your velocity is going really high negative to 0 to really high positive to really 0 or to 0 to really high negative. So it would actually be a sinusoidally decreasing age, but it would only start to decrease when you get near the humps, the negative hump, the trough, and the crest. In the middle part, the speeds are going to be too low compared to the speed of light because they're approaching 0. But yeah, if you're vibrating back and forth where your peak speed is something like 3/4 the speed of light, then yeah, you're still going to get time, but it's just going to be reversing. And of course, your neck's going to be rung off. But yeah.
Yeah. So by that idea, if you had a stationary anchor with a long spring and someone is attached to it and the spring is just oscillating, so by the nature of that person traveling at an appreciable percentage of the speed of light, the part of the spring that is attached to them is also moving at that speed. So yeah, would that mean that like the rate of corrosion and degradation of the spring, like it would start to rust at the base of the spring by the anchor, and then the spring out at the end would still be pristine after a while, basically? Yeah. Like it would.
Yeah, it still gets to age during the low speed periods, but not nearly as much because the high speed periods are going to be less aging.
Kind of interesting.
Yeah, they've even done this. Like they took an atomic clock and flew it on the Concorde around the Earth and used relativity to predict. And the Concorde's fast, but it's really slow compared to the speed.
Well, yeah, it's only like what I think 1,400 miles an hour or something like that.
Which is Mach 3 or something, but still that's not an appreciable factor of speed of light, but it's good enough. If you use an atomic clock, you can see the time change
accurate
in those
enough,
6 or 7 decimal places. So that's the only way they could do it in real time, and they did it and found out it was exactly what relativity predicted.
I think they also took it was either an atomic clock or just like a well-made digital watch, or no, it was a well-made mechanical watch, I think. And then they somehow factored out mechanical interference and cosmic radiation, and then they had it in the space station that is orbiting much faster than even the Concorde could move,
Right.
and they got the same results. That was a long time ago.
And that one still doesn't have to be that big of a factor, but yeah, you can definitely detect it because that's got double whammy. One, it's moving fast, and two, it's in a gravitational well at a higher altitude than earthbound. So it actually, its time changes different. So it's a general relativistic correction as well as a special relativistic correction.
Okay. Although you mentioning the gravity well reminds me, I'm sure you've probably seen Interstellar.
Yeah, that was great.
Did you ever read about so the music has this very slow kind of metronome tick to it when they're on like the water, the tidal wave planet?
Yeah.
I read somewhere that like each tick is I think a month passing in real time by comparison to the relativity of them being so close to a black hole.
Yeah, and in fact, Kip Thorne, he just won the Nobel Prize. He was their expert on that. He did the calculations for it. He said, I got like 5 publications out of making that movie. So he was able to solve some really big, problems, or at least interesting problems, to make sure the physics was right in Interstellar. And of course, he later won the Nobel Prize. Him and Barry Weiss and third person I can't remember right now. But anyways, they won the Nobel Prize for the first detection of a black hole colliding with another black hole. But yeah, that was good science on that one.
I remember reading about that.
Yeah,
what happens in that case? That like do they just kind of like just or do they orbit for a while? I mean, I'm sure they orbited,
spiral around each other. In fact, that's what the signal looks like. If you look at the signal, it's just a nothing, and then like that whole is like in
that was
10 to the negative 9 seconds.
Yeah, orbiting for a unbelievably short amount of time, and then they consume each other.
Yeah, if you ever taken a wooden ruler and hang it off the end of your desk and you pop it, it goes wow, and then you pull it in real fast. When you do that,
it speeds up the oscillation because the length of the oscillation is getting shorter.
Yeah, that's exactly what happened with them, at least in terms of a gravitational radiation signal that you got from them. Is it goes really high amplitude to low amplitude, and it did it, like I said, like in 10 to the negative 9 seconds, and it's just really incredible. And not only that, we're talking space changing by no more than like the wavelength of light. So the space compressed. That's what the gravitational wave is the literal space compressing, shrinking. And it didn't change, over a distance of a mile. It didn't change, but 10 to the negative 9th or 10 to the negative 10th meters. I'd have to do the calculations or look it up. But some god awfully small atomic size, basically.
I think I remember reading about that, actually. They built a structure underground somewhere with like mile or 2 mile long tunnels with mirrors hanging at the end of them.
Right.
And they used the mirrors to, like, they were shining a light back and forth between the mirrors, and then used the distance that the mirrors moved, which was like the width of a proton or something ridiculous like that.
Yeah, it's called LIGO, L-I-D-O.
Okay. Yeah, they were doing that to measure gravitational waves. And I was actually wondering about that. When they say gravitational waves, do they mean to imply that like it behaves like a wave where it's traveling, like gravity will affect one part of space before it affects the other part of space, like gravity moves?
Yeah, it propagates outward. You remember, gravity is not really a force. I've mentioned this to you before, but in terms of general relativity, gravity is really a deforming of space. Space being x, y, or x in and out, y left, right, z up and down, plus the time dimensions, the fourth. That overall distance in that space time gets shrunk.
Mm-hmm.
And when it gets shrunk, it's in a trough. And when it gets stretched, it's in at a crest. And in between is at the zero line. And that propagates outward at the speed of light. And that coming here, by the time it gets to us, from 27.8 million light years away or whatever, it's spread out over all space, equidistance from there to us. So in other words, it makes a giant sphere, 27.8 light years or 27.8 million light years in radius when it gets here, and it hits them in order one by one. The farther and farther it goes, the longer and longer in time. And not only that, it seems to defy conservation of energy and conservation of momentum, because the momentum of the two particles, or the two black holes, if you add those up and then find the momentum of it after they've collided, it's actually smaller than the initial two added. But that's perfectly reasonable, because remember, part of that energy and part of that momentum went out in the gravitational wave, and that's what we're seeing.
I was thinking maybe it was accounted for by the ridiculous amount of spinning, like the moment of the black hole, basically.
Yeah, and it does do a ridiculous amount of spinning. Imagine 25 solar mass black hole, and I think the other one was like a 12 solar mass, somewhere around there is the two numbers. And they ended up making something well under the sum of those two masses, because that mass was converted to energy via E equals mc squared, and then that propagated out as a wave.
So by the nature that gravity is a wave that travels, one could, I don't know what situation this would be relevant in. I guess you'd need some kind of godlike being or force. But if somebody were to just wink the sun out of existence, then we would continue orbiting for a few minutes, effectively,
yeah, 8 minutes.
until the lack of gravity reached us.
Yeah. Yeah, it would take about 8 minutes. That's about how long light takes to get to us from the sun. So yeah, it would take, if it just blinked out of existence, we would continue traveling the way we were for another 8 seconds. Or excuse me, 8 minutes.
I'm not sure what other, I guess, implications that could mean, because I don't have a PhD, but that's pretty interesting.
Yeah, and not only that, here's the neat part. The center front of the sun, wherever we're at, the part closest to us is the center. That would go out first, because the whole thing, if it just disappeared, the first part you'd see disappear is the part closest to us, and then it would spread outward like this. So we'd see the middle get a black dot, and then that black dot would grow until the whole sun was gone.
Yeah, because like from the midpoint of the sun to the outer edge of that curve, that's a pretty appreciable distance. So you could probably watch it if you had something trained on the sun at the time. You could probably watch it happen as it just obliterated itself.
Yeah,
it'd be pretty interesting. It's cool.
Yeah, it's some pretty cool stuff.
All right, thank you for your time. I guess so. I was actually wondering. I heard from Miss McIntyre, my previous class. She said that she was saying that there's an announcement on the TCC website that there are no courses tomorrow. Does that mean no in-person courses, or just like no courses?
Oh, I hadn't heard anything about that.
Because it's election day.
Oh yeah, that probably means no. I forgot about being election day. Yeah, that's probably just on face-to-face classes. I will check my calendar to make sure. If I find out that everybody's out, then I will send an email to everybody.
Yeah, I was just wondering. I only have the one course, but I can't ask him because I don't have that course today. So I was just curious about that.
That's an online class for you too?
Yes.
Yeah, I'd email them just to check, but I'll check for you as well, and I'll send out an email to all my students to let them know.
Gotcha. All right. Thanks, sir.
No problem. Have a good one.
You too.